Ladies and gentlemen, I think we finally have a working track retraction system for WALL-E. This is the most exciting part of this project. It was the part that made me the most nervous because it's such a challenge, but we have a working prototype. I did break it, but in the meantime, I can show you what I've done. So check this out, okay? This right here was garbage. It didn't work. I tried pneumatics, and this was a fun idea. That also didn't work. I thought an electric actuator might give me a better result. Nope, not enough room. But this guy works. What's funny though, is if it wasn't for the journey, there's no way I would have got to this destination. So I gotta take you back to the beginning and I'll share the story with you of how we came up with this design. Like I mentioned before, I broke the prototype, but I am running out of time to get this video released, deadlines and all that good stuff. So I need to catch you up on what this series is about because this is part 2, and we'll do that while I try to, as quickly as possible, rebuild the prototypes that I just broke. This is WALL-E, or this is just a shell from part 1 where we were trying to look at what kind of space do we have to work with? This guy's actually hollow on the inside. The goal is to build a machine as if WALL-E was a real robot. I am not a prop builder. The goal is not to make, a pretty painted object that looks like WALL-E. I want him to have retracting legs. I want him to be closer to an industrial machine, but still giving you the feel that you get when you look at WALL-E from the movie. That's the plan, at least. This is asking a lot as I'm discovering every step of the process. So anyway, WALL-E's a challenge. I've tried a whole bunch of prototype legs. A lot of them failed, but we can learn from our failures. And that's the goal of this video, to show you all the things that went wrong as we work our way back towards what I think is going to be a working version. The prototype worked, at least. We'll see. Okay, this guy is pretty loud, so let's switch to B-roll and we'll keep talking. One of the first things I do when I'm designing a machine is I try to find out if anyone else has solved this problem before. So I did some homework to see, has anyone designed an industrial machine, like real mechanical equipment with retracting tracks? And it only took me a few minutes to find this backhoe with tracks that slide in and out to adjust for different widths. Now, of course, this is not full retraction, but these tracks are literally just being pushed straight out and pulled straight back in. That's a really simple design. In fact, when I bought this WALL-E toy, it works very similarly. The tracks just go straight in and then straight up. So this is where I started. What if I had 2 separate mechanisms, one that makes the tracks go down and a separate one that makes the tracks go out, right? Now, of course, the backhoe is using hydraulics, which is a little bit messy and really slow. Electric actuators are also pretty slow. So I thought, what if we use pneumatics? Now, I'll wait for the noise. Now, we have a bit of a problem with storage. I've got to carry the air with me, right? Carrying around compressed air is not going to be easy. But if we had a way of using CO2 canisters or some sort of method for making the compressed air portable, it will be really powerful and explosive. Every time we see WALL-E retract into a box inside the movie, he is reacting, right? He's afraid. And so if we want to capture that sense of this happening quickly, then pneumatics is a good way to get that kind of speed. I also love the sound of pneumatics. It's got a nice sound every time you actuate the actuator, giving us that industrial feel, which is another thing that I want people to sense. When it happens, I want you to feel something, right? In fact, I've got a great clip of my wife reacting to using a pneumatic actuator for the first time. We've got 2 actuators here, and it's all controlled with the foot switch.
Ooh, what kind of?
You can step on it.
Wait, right now?
Yeah.
Is it set up?
Yeah.
What happens? Why?
This is like the best possible clip to explain what I'm trying to accomplish. I recorded this years ago, but even just watching it, I still enjoy reliving this moment with my wife. And that's what I want people to experience when they meet WALL-E. I want them to feel something, and I want them to remember meeting him. This is not gonna work, but it was fast. Okay, there's another problem that we haven't addressed yet. At least you haven't seen the solution yet, unless you watched part one. What's the problem? Well, we've got an enormous amount of sliding friction trying to push these rubber treads left and right. Right now, we're using plastic treads, which slide a little better, but even this is causing quite a bit of friction. Once we switch to rubber, the traction sideways is gonna be enormous, and we need to overcome that. Well, one problem at a time. I have a solution that I'm working on. I think it's gonna work pretty well. Again, I showed you a big clue in part number one as to how I plan to do it. In the next episode, you will see the full solution. But for now, we need to address their retraction mechanism because that's a big enough problem all by itself. One problem at a time. All right, so that you can understand the problem with electric actuators, I want to change the setup here a little bit. And the problem is actually the same with pneumatics and electric. I was considering them at the same time, knowing that pneumatics brought all sorts of complications like needing to have compressed air and where am I going to keep all this air and so on. So electric will be better in that sense, but like I mentioned earlier, it's slow. I'm going to raise the table up. The actuators in this table are the kind you would typically buy unless you bought the really high-end servo style. Here we go. There are 4 actuators, 1 at each corner. Yeah. So we can solve the speed problem, but the problem we can't solve is the length. The length of the actuator has to be at least the length that I need the wheel to travel. So that would be from here to here, right? The problem is the base of the actuator also has to be at least that long, plus a little bit for the mechanisms inside. And that's what you see here. This section cannot be longer than this section. Are you starting to see the problem here? So I spent a little bit of time thinking about how do I get more travel out of my actuator? And then it hit me. Okay, check this out. So here is the full length of travel for this actuator. Just under 11 inches, that's 10 3/4. And if you want to see that in metric, 27.5 centimeters. We're gonna put this right at the level of this bar so that it's easy to measure. And the new distance is off the charts. I need a longer ruler, 20.5 inches. So then what did I change? Basically, when you fix the belt on this end and you move the pulley in the middle, every time you add 1 inch on this side, you also need an additional inch of travel on this side to accommodate the new length of rope. Therefore, we both increase the speed of movement and we get double the travel for half the length of the actuator. And even though I was super excited about this and I thought, I have nailed it, this is gonna work, the problem was still lingering right there in front of me. Let me show you what I mean. Once you take into consideration that I've got 2 sets of tracks, I've got to have room for this actuator movement in this space, not in this space. So what I actually need is something small enough to fit in between the tracks. So I was back to the drawing board. So this bugged me for a while until I had one more idea, which also didn't work. And that is, what if I took a really short actuator, something like this. This one's pneumatic, but we would use electric, okay? You get the idea. Short stroke. Move it up high so that it's out of the way of the wheels. And then attach it to a lever. Now I can use this lever to multiply the length of travel. We don't need a pulley now. We can just push this short end and get a much longer stroke. But there's nowhere I can put it that would allow me to position the wheels the way I want. If I put it here in the middle and pull on it this way, as you can see, I've created an arc. And this lifts the wheels up instead of pushing them straight out. I really need linear motion. If I move it over here, not only is the wheel interfering when it's in the lower position, I've still got an arc motion at the bottom, which I don't want to change the contact angle. And finally the clincher. If I move everything up here, I can't retract the head because I also need this space for the arms and the head. Yep. So then I thought, okay, this is a space constraint problem, and you've done this before. If you scroll back to some of the earlier videos on my YouTube channel, you will see all kinds of projects based on space-saving devices. I made this pull-out drawer system that would allow me to tuck my table saw underneath my workbench because I needed the space. I made this flip-over workbench with linkages on the side. I did this so that I could put two tools in the same workspace to save space. And so I'm thinking, okay, it's a space-saving problem. How do I get everything I need into this tiny space? We can do this probably with linkages. The easiest way to design linkages is to just sketch them out first and get the concept on paper, and that'll help you troubleshoot very quickly. So let's jump into Onshape. I'll show you some of the linkage designs I came up with and the one we finally decided on. Okay, so right now you can probably make out Wally's profile, and you can see that there's a bunch of sketches on the screen. Early in the model, you can see I've defined a bunch of parameters. Basically what I like to do is whenever I'm designing something with a parameter I know I'm gonna change a lot, I go ahead and create this variable right here at the top. And that way I only have to change it in one place. So if I change the tread height to 11 inches, there are several other parameters inside this model that are all based on that height, and they all change automatically. So it's a really powerful tool. Instead of like trying to find everywhere that something is affected by me changing that number, I can just change it in one place. And so you see all those here at the beginning of my tree. This first one may be kind of hard to tell what's going on, but basically this is a scissor jack. And these lines represent the dimensions, the space that that scissor jack will take up. That didn't work. It was going to be too large. This one is basically the design I showed you earlier where I would just connect the tread to a lever and then swing it out to the left. As we saw earlier, that didn't work. This is the first one that I kind of liked, which is this, what I'm just calling the side scissor action. The reason I don't like this design is because it's not nearly as strong as I would like it to be. Remember, all of Wally's weight will be bearing down here. I didn't really like the way the weight was distributed there. And now we're getting to the two designs that I really like. The first one is this linkage here. So again, there's a lot of lines here, but if I drag where the tread is, you can see the motion. This will slide in, and when I pull it out, it'll extend out to here. But you can see this doesn't take up nearly as much space as the other designs. I also like the fact that it's really low profile so that you don't actually see it when he's riding around. You just see his treads, which is what he looks like in the movie. Probably the main thing I don't like about this design is that the tread can pivot around this point. I don't expect this to be a problem when he's just driving around, but when I'm retracting the tracks or extending the tracks out, I'm dragging it sideways, which might cause them to tip because it can tip around that pin. I could add something that would prevent it from pivoting, but then I'm just getting closer to my next idea, which is the 8-bar linkage. So you can see the action of the 8-bar linkage here, which mechanically speaking is way cooler looking, right? It's definitely more interesting. Problem is, this is far more complicated, and I just feel like there are more things that can go wrong. I do like the fact that it will hold the treads upright, it moves linearly, it's strong enough. Probably the main thing I don't like is Wally needs to ride higher off the ground now. You can see where the profile of his body is, and when you extend this out, that's how far out the tread needs to go. But now this portion down here needs to come all the way up to here to clear his body. There's no reason I can't do that, I just don't think it looks as good. So that's the main drawback to this situation. Riding higher, and then also the fact that this mechanism in general is more complicated. So I've decided I'm gonna do both. I'm gonna try both systems and see how they work. This is actually the first full project that I've designed from scratch in Onshape, and I gotta tell you, I'm pretty happy with the progress so far. This is working out really well. I mean, I'm sitting here in the shop on my MacBook and I've got full access to my 3D model. I've got parametric design. I've got all the things that I want, and it's nice and portable. it's hard to find a complaint. I would say the only thing that was really hard to get used to is the persistent select. Once you click on something and click on something else, it stays selected. It's just a different rewiring of your brain and how you're used to using that particular function. Also, you don't use save. Everything is just automatically saved all the time. Like you can undo as many times as you want. It's automatically saved and it never crashes. Okay, that's huge actually. I have not had a single crash since I've been using this. That part is pretty fantastic. Not only do you have a free version if you are, using it for non-commercial purposes, the professional version, which is what I'm using, is very robust and it gives you the tools that you need. So if you want to try out Onshape for 6 months, they have a discovery program where you can try it for free for 6 months. I want to say thank you to Onshape for encouraging me to try out the software and also for sponsoring today's video. All right. Let's get back to Wally. So generally when I'm making prototypes, I'll start with just the sketches that you just saw. Then I will turn them into linkages like this to cut out the flat patterns. It's just a really fast way to double check that I'm not crazy, that this will actually move in real life. And then I'll make a more functional prototype. So here's a quick build montage of what that was like over the last week. And then you'll be all caught up to where we are today. And here we reach the stage affectionately referred to as integration hell. As soon as the mechanical, electrical, and programming all have to communicate with each other, you are definitely going to have a problem. And no matter how many times I've visited this place, it's hell every time. Well, that's just great. The color scheme is different for this motor. Yeah, I should have known better. I've had this problem before. That's why the motor won't spin. Okay. I gotta go eat something. I'm too hungry to focus. Let's go do that, and then we can fix problems. Will this work? I have no idea. Oh, stop that. Okay, so that's quiet. Okay, that's set to only go halfway, so that's good. So I can increase the range, and then we're almost there. All right, ladies and gentlemen, moment of truth. God, this is all Frankenstein. Yeah, that's as far as it should go. Ah, okay. Yeah. I think we got a retraction system. When I'm in this prototyping stage, I try to avoid getting bogged down in the details. For example, we can get rid of the jittering noise by adding a dead zone to the program so it's not constantly trying to update its position. I plan to use a servo motor instead of a stepper motor, which is also much quieter than this stepper motor that we're using. Right now, I don't have the bushings installed, so the shafts can wiggle a little bit, and therefore the linkages aren't moving perfectly in sync. But again, these are things I can ignore. However, this is integration hell. You do have to stay vigilant because things will go wrong, just like this. Okay, that took a minute. Oh, I left them both plugged in. Did not mean to do that. Okay, gotta connect it to do this. Okay, wow. Okay, that was bad, but we got a proof of concept. It works. You know what? Total victory. No big deal. I would like to toy around with this a little more, but we got this part figured out. Let's move on to the next step. Ladies and gentlemen, we got parts. Oh, we've got our carbon fiber arms, and these are titanium. So you might be wondering, why am I ordering titanium gears for Wally? My original plan was actually to make all the parts out of carbon fiber, but when I saw the price of the titanium next to the carbon fiber, I said, Wally's gonna have titanium gears because it's awesome. And that's all the reason I need. So there you go. Send Cut Send is like my go-to option for manufacturing on demand when it comes to sheet metal. I mean, they offer other services too, but if I need anything cut out of a flat pattern, including titanium apparently, you can order it from Send Cut Send, and the service is fast and incredible. So link in the description if you find yourself in need of such a service. All right, we are ready to assemble our parts. Let's get back to work. Enough partying. In order to test the retraction system completely, I need a working base. But the base is probably the most complicated part of this machine. I'm nowhere near being done designing it. Therefore, I'm going to 3D print this mock-up to give me some kind of platform to work with. If you have access to a resin printer, this is really the ideal tool for making prototypes, primarily because the material is isotropic. Isotropic basically just means the material has the same strength in all directions. If I wasn't fortunate enough to have Formlabs send me this printer, I probably would have machined this part out of metal rather than try to 3D print it. And that's because FDM printers, the kind that squeeze the plastic through the nozzle, creates layer lines, and the part is weak in that plane, thus it's not isotropic. Resin printing gives you a lot of options in terms of materials and frankly produces some fantastic prototypes. The level of precision and detail that you can achieve is also very high. The trade-off is there's far more post-processing. As you can see, I have to wash the liquid resin off of the part, then you have to bake the part for a while after it dries. There's more cleanup involved, and in general, the same size part will cost more to print with a resin printer than it does on a FDM printer. At this stage of the project, something weird happens where we transition out of integration hell into something like a mechanical nightmare. I keep running into these small mechanical issues where I need to make a slight change. I even had to change my gears. I'd remake the parts, reassemble everything, find another small problem, and do it all over again. It reminded me of that movie Groundhog Day where he tries to fix the problem from the previous day, something different goes wrong, and he's back at it again. Oh, that's interesting. Okay, maybe this will be the final prototype and then we can start machining the real thing. So you may have noticed this looks a lot like the original design. I assure you there are some differences, but the main thing is I've rejoined the linkage to the gear. The reason I separated them to begin with is because my carbon fiber linkages came in and I wanted to use them for this setup. So I just added a fastener hole. But you can see I've got some play here. I've tried tightening this, but if you tighten it too much, it crushes the plastic. Can't do that. So I just said, let's just make them one solid piece. I'll take this out until I'm done testing. And then when the final gear design is completely done, I will epoxy these two pieces together so there's no chance of them being able to slip. I've also reprinted this back wall that you can see back here to deal with the slop in this hole. So hopefully those two changes will allow us to get nice full retraction, and then we'll know for sure that this is gonna work exactly like we want. So let's get all these parts installed. Oh, another thing that I changed is I switched from Tough 1500 to Tough 2000. The main difference is that the Tough 2000 is a little bit stiffer than the 1500. right. 3, 2, 1. Yes! Oh my God. Oh, okay. Okay. Okay, that's good. Yeah. Yeah, this is good. This is real good. Let's see that one more time. I can play with this all day. Come on. Oh, you are beautiful, my friend. But that's full weight bearing right there. And it's doing it. What's so great about this is I'm using a 20-to-1 gear ratio right now, but this guy right here, this is a strain wave gear with a 100-to-1 gear ratio. Because I anticipated I might have trouble with this, which this is looking way better than I thought so far. I've already made an adapter plate. That's what you see here. This motor has the same faceplate as the motor that's in there now. So I'll just swap these out. And then we got 5 times the torque. This shouldn't be a problem at all. So good. Yes. One more time. Full weight bearing. Oh my gosh. Oh man. So much pain to get to this point. And we are just working on the base of the robot. But we're gonna get there. One problem at a time, right? One problem at a time. I love it when you guys get feedback in the comment section. I always find it really helpful. So I thought I would share with you a few design notes or requirements, if you will, here at the end, just to make it easier for you to be on the same page with me. Number 1 is the weight requirement. Right now, I am setting a limit of 150 pounds or about 70 kilograms for Wally's total weight. The primary reason for that is shipping. I want to be able to send him somewhere without shipping him freight. And that means I need all the parts to be really lightweight, but also very strong. That's why the legs are made out of carbon fiber, for example. And I plan to extend that concept pretty much throughout the whole build. It'll be, lightweight materials like aluminum, carbon fiber, and so on. I mentioned earlier that there's a pin that allows the wheel to tip left and right, and that there were some ways to manage that. The 2 ideas that I came up with was some type of ratcheting mechanism that can be disengaged with a little tiny hobby servo motor. Similarly, I thought I could just push a pin into place that would lock into the linkage when it's fully extended, and it would serve the same purpose. You won't be able to tip the wheel and it's locked, but that means more complexity in terms of the number of parts and more programming complexity because I need to have an interlock that tells it to make sure the pin's not in place before you retract. That's what I was trying to avoid. But I really like this design, so I'm probably going to do something like that. Right now, I'm just commanding the motor to move so many degrees and stop, and then move so many degrees in the other direction and stop. But in the final design, it'll be safer to have some type of sensor at both ends of travel so that the motor can run until it hits the sensor and then it stops. Basically a limit switch. And the same at the top and the bottom. That'll be safer because I don't have to worry about if the motor loses track of where it is, power loss, it stops somewhere in the middle of travel and then comes back on and wants to go the full number of degrees. I can prevent that problem if I have limit switches that will tell it where the top and the bottom is. There are a couple more ideas that I explored, which I just didn't have time to show you in the video. I felt like the video was getting too long. For example, I was working on this spring-loaded mechanism, which would push the legs out really fast with a spring and then pull it back in with a cable. It was basically impossible to find a spring which had the right amount of force, but also the right amount of travel, and on and on. So engineering is so fun and challenging, and I wish I could share it all with you, but I didn't want the video to be an hour long. I was hoping to give you something a little more concise than that. But you get the idea. There are many ways to tackle this thing, and I tried quite a few of them. This is what I ended up with. So we are ready to move on to part 3, where we're going to be working on the tracks themselves. So it may not be very long before Wally is rolling around here. I mean, he won't fully look like Wally yet, but maybe he'll be mobile. Anyway, thank you so much to my patrons and my YouTube members. You guys are a huge part of helping me do what I do here, and I'll see you in the next episode. Thanks for watching.